In the warm-up, you reviewed imaginary and complex numbers. In this segment, we're going to learn how to add and subtract with complex numbers. As you work through this segment, think about the difference between working with real numbers and complex numbers. Is it the same or is it different, and how? Also consider the properties of the real number system and how they compare to the properties of the complex number system. Let's get started. The complex number system, like the real number system, constitutes what we call a field. Numbers in a field conform to a set of rules or patterns of behavior. You're already familiar with the field properties of the real number system. These properties also apply to the complex number system. Remember that all real numbers are considered complex, as well as imaginary numbers. Those are also part of the complex number system. Let's take a look at an example for adding complex numbers. When we add two complex numbers, right, we have an A and a BI, a C and a DI. We're adding them together. The first step is to remove the parentheses. So I'm going to rewrite this as negative 12 plus 4i plus 9 minus I. The next step is to apply the commutative property. I basically want to move things around so that my imaginary terms are close together and my real terms are close together. So I'm just going to commute these two and get negative 12 plus 9 plus 4i minus I. Now that I have my terms together, I'm going to go ahead and group these terms using the associative property so that I can add the terms that are like. Alike meaning I'm going to add my real terms and I'm going to add my imaginary terms. And simplify means I'm just going to add them together. So I end up with negative 3 plus 4i minus an I. Remember, the distributive property actually allows us to take out that I and look at the 3 minus 1. I end up with, 4 minus 1, 3i. So the result is negative 3 plus 3i. The idea here is to group the real numbers together, add them, and then group the imaginary numbers together and combine them, and I'll end up with my complex result. Let's take a look at an example for adding. Remember that when we subtract real numbers like a minus b, it's the same as adding the opposite of the number that we're subtracting, a plus the opposite of b, or negative b. So if it's negative, it becomes positive. If it's positive, it becomes negative. So for example, if we had 15 minus a negative 2, it's the same as adding the opposite of negative 2. So the negative became a positive, and we end up with 17. As it turns out, for complex numbers, it's the same rule, the same definition for subtraction. To subtract two complex numbers, a plus bi minus c plus di, we add the opposite of c plus di. The opposite of c plus di means you have to take the opposite of c and the opposite of d. See these two negative signs? So for an example, we have 10 minus 3i subtract negative 6 plus 7i, we need to take the opposite, right? Add the opposite of the entire complex number. So that means positive 6, negative 7i, or plus a negative 7i. Now we can just add our complex numbers. We already have a method for that. We're going to regroup here and get our real terms together and get our imaginary terms together. And we end up with 16. Now let's see, negative 3 minus 7. Now I have another subtraction, adding the opposite. And we have, that's negative 10. I'm just going to make this minus 10i. And we're done. Let's revisit our lesson question. How is operating with complex numbers similar to or different from operating with real numbers? In a previous segment, we learned how the real number system is really similar in properties and process to adding and subtracting with complex numbers. In the next segment, we're going to focus on multiplication and division. Let's get started. Take a look at how to multiply imaginary numbers. In this problem, we have two imaginary numbers that we're asked to find the product of, 3i and 4i. The first step is to write out the factors. 3i has two factors, 3 and I, 3 times I, just like 4i, 4 times I. The next step is to apply the commutative property. This is really similar to addition when we want to group everything that's like together. So I am going to commute I and 4 so that my i's are together and my real terms are together. Then I'm going to apply the associative property. The associative property is going to allow me to group the terms that I want to multiply together, reals, imaginary. Then I multiply. 3 times 4 is 12, and I times I is I squared. But we know that I squared is equal to negative 1. So I can replace I squared with negative 1. When I replace I squared with negative 1, I always use parentheses because I never want to misread this as 12 minus 1. The last step is to multiply. 12 times negative 1 is negative 12. And I'm done. In this problem, we're asked to multiply complex numbers, meaning we don't just have imaginary pieces, we also have a real that's added onto this imaginary. To do this, just like real numbers, we would distribute this imaginary number throughout. So negative 2i times 6 and negative 2i times 7i with the subtraction in the middle. You end up with negative 2 times 6, negative 12i, negative 2 times 7. I'm going to make this subtraction carry over. Negative 2 times 7 is negative 14, parentheses, so I don't subtract, I squared. And I end up with negative 12i. I'm going to deal with this I squared right now. Right? Again, the parentheses are coming in handy because I don't want to subtract 1 from negative 14. I want to multiply. Negative 12i minus 14, right? And I'm done. If I wanted to, I could commute it so I could get my imaginary part to be second, but either of these are acceptable. Most often, when you're asked to multiply complex numbers, a usually isn't equal to 0. What that means is you usually have something that's being added on to your imaginary term. And in this case, we're really just multiplying two binomials as if I was just a variable. We know it's not. We know that I is the imaginary number and has special properties, but we can still use FOIL, just like we do with real numbers, to figure out what our product is. So let's get started. Let's do FOIL. We have our first terms, 8 times 3, which is 24. And then we have our outer terms, that's O, 8 and negative 7i, which is negative, 56i. And then we have our inner terms, 4i and 3 plus 12i. And then we have our lasts, 4i and 7i. So that's 4 times negative 7, which is negative 28, and I times I, which is I squared. So then we want to simplify. We can go ahead and combine these terms here. 24 rather. Let's see, negative 56 i's plus 12 i's. I'm just going to subtract these numbers. Is that right? Yes. And I know it's negative because the larger number was negative. I's minus 28 I squared. Now, I can go one step further because I'm squaring I. And remember that I is equal to the square root of negative 1. And if we square that, that's like squaring this. And I get negative 1. So this is the same as 24 minus 44i minus 28 times negative 1. So I end up with 24 minus 44i plus 28. Now I have two more terms that I can add. 24 and 28 is the same as, 52? Yeah, minus 44i. So the result of two binomials should result, not two binomials, the result of multiplying two complex numbers actually results in a complex number. So when you're given a number, a plus bi, right, that's our complex number, its complex conjugate is this number, a minus bi, or a being combined with the opposite of your I term. The product of complex conjugates has an interesting result. So let's investigate here and multiply this out. We'll use FOIL again, and let's take a look at what the product of complex conjugates looks like. 7 times 7, 49. And then let's see, first outer, 7 times negative 2i. Inner, 2i times 7. You might already be seeing what I'm seeing, lasts, minus 4i squared. Take a look at the middle two terms. These terms are opposites because we made these opposites. So we end up with 49, nothing in here. This makes a 0, and the 0 just kind of cancels, quote unquote cancels. But now we have an I squared again, and that's negative 1. So this is the same as 49 minus 4 times negative 1, which is just 49 plus 1, which is, oh, not 1, 4. Negative 4 times negative 1 is 4, equals 53. So the product of two complex conjugates, right, a complex number and its complex conjugate is going to end up real. It's not going to have an imaginary part because creating this plus minus is going to make that middle term go away. It's similar to a difference of two squares where the middle terms, they cancel or they create a 0 and you lose the I because then the I gets squared and we know that I squared is going to give us this negative 1. When dividing complex numbers, we multiply both the numerator and the denominator by the complex conjugate of the denominator. Really what this means is to ensure that there is no complex number in the divisor of our fraction. So if we're asked to simplify I over 7 plus 2i, we're really being asked to divide I by 7 plus 2i. So when we're asked to simplify, that means to make sure that there are no i's, there are no imaginary numbers in the denominator of our fraction, meaning take care of that division. To do this, we're going to get rid of this fraction bar, or we're not going to get rid of the fraction bar, pardon me. Let me show you how we're going to rewrite it. We're going to multiply by the complex conjugate, multiply both the numerator and the denominator. So what's the complex conjugate? Remember, we did this from our previous example. The complex conjugate is keep the first and take the opposite of the imaginary term. And I'm not going to show you how we FOIL this out because we did this already. But notice this is our fancy version of 1, right? This is just 1. So I'm allowed to multiply by this. So it doesn't change the value of my expression. So I'm going to take this I and I'm going to distribute it through my complex number. And I end up with 7i minus 2i squared. Now we already know what happens to the denominator of this fraction. These cancel or create a 0. This I squared becomes a negative 1. Multiply by, this shouldn't say 2 actually. 2 times 2, this should say 4. That's okay. Here's a 4. Negative 4 times negative 1 gives us that positive 4, which gives us a 53 on the bottom. But on top, we have this I squared, which is, again, negative 1. And negative 1 times negative 2 is a positive 2. And we end up with 7i plus 2. And obviously, I mean, not obvious, but convention is to make sure that the I term is written after so that we're expressing it as a complex number. So I might choose to write it like this. Both answers are correct. And really, all we needed to do was get rid of that denominator. It's like rationalizing the denominator when we have a radical down there. We use this complex conjugate to get rid of the I as part of our denominator. Similarly, we might be just asked straight out, divide 4 by 3i. So you can do the same process. You can write it as a fraction, 4 over 3i, right? Here's our conjugate. Now, 3i doesn't have an a part, but that's okay. It still has a conjugate because I can write it like this, right? A is just 0 here. So to take the complex, to see the complex conjugate of this, I'm just going to take the opposite of my imaginary term, which is why you see negative 3i here. Remember that this is just a fancy 1, right? Multiply through. 4 by negative 3 is negative 12. 3 times negative 3 is negative 9. I times I is I squared. And then this is negative 9 times negative 1, which gives us the 9 down here. And then we're just simplifying here. 12 over 9 is the same as 4 over 3. Now, just to prove to you that we got the right answer, if we divide two numbers and get a result, I should be able to multiply this by any one of these factors and get 4. So let's try to multiply this by 3i and see if I can get 4. Sorry, if I multiply by either one of these, I should get the other. Notice that these 3's cancel or become a 1. I times I is negative 1. So we negative 4 times negative 1, and I end up with 4. So I know that this leads me to the right answer. So when we're dividing, set it up like a fraction, whether it starts there or it doesn't. You can always set it up. And we want to multiply the top and the bottom, the numerator and the denominator, or a fancy version of 1 that has the complex conjugate. We take the opposite of the I term and then simplify.